So the next thing we're going to do is we're going to take logic gates. We'll take a pair of NAND gates. We'll do something I'm going to call logical feedback to basically build a device that does something useful. So I've got the two NAND gates. Inputs A and B go into them, and then the output of the A goes into the B NAND gate, and the output from the B NAND gate goes into the A NAND gate. And these two outputs are X and Y. So this would say X is equal to A and Y is equal to B and X, and it's a NAND, so they're complemented. So, and that looks like kind of a crazy circuit there. I mean, how do you solve that kind of thing there? What we need to do is we need a choice A, B, X, Y as input, where the X, Y as output is consistent with that, with the input. And what does that mean? So you can imagine A, B, X, Y. We can have zeros or ones everywhere here. So there's 16 possible combinations of A, B, X, Y with all the zeros and ones. And we could write down all 16 of those. And then for each one of those, we could calculate A and Y complement and ask, is it equal to X? And we could do B and X complement and ask if it's equal to Y. And if it is, then it's consistent. And if it's not consistent. So let's look at a couple of those here. We'll do A, B, X, Y. And then we'll calculate A, B. And really we want to know, is this X and is this Y? So let's just start with 0, 0, 0, 0. So there's four things. And now A and Y, 0 and 0 is 0. Complement is 1, so we get a 1. And that 1 certainly doesn't look like X. We can do the other one too. B and X, 0 and 0 is 0. Complement is 1. Get a 1. This one doesn't work. So that's not a consistent state. Try something different. 0, 0, 0, 1. We're going to have the same problem if we do A and Y. Let's see, A and Y, 0 and 1. It's going to give us 0. Complement's going to give us a 1. So we're going to get a 1 there. That's not consistent with X. And then for the B and X, we're going to get 0, 0. We're also going to get a 1. That's partially consistent, but this still doesn't work. So, no. We'll try something else. 0, 0, 1, 1. Now, 0 and 1 gives us 0. Complement gives us 1. Same thing for the other one. And here, the 1 is consistent with that, and the 1 is consistent with that. So that works. So this particular combination is a consistent combination. We can go through all 16 of these, and it turns out that there are 5 combinations that are consistent. I'm going to just write them down. So A, B, X, and Y, or 0, 0, 1, 1. We have that one from above. 0, 1, 1, 0. 1, 0, 0, 1. 1, 1, 1, 0. And 1, 1, 0, 1. 5 consistent combinations. And what we're going to do with this is we're actually going to consider 4 of these as important. We'll take those 4, the green box. And the reason I chose those 4 is the two outputs are complements each other. If X is 1, Y is 0. If X is 0, Y is 1. And this one is different. So we've got complements. And now I'm going to rename some of those inputs. So I'm going to rename those inputs. I'm going to take the A input. I'm going to go to something I'm going to call set. The B input, I'm going to go to a reset. The X output is going to go to Q, and the Y output is going to be the complement of Q. So I'm going to remap this into this particular truth table here. And so I'm going to have set, reset, Q, Q bar. And I'm going to have 1, 1, 1, 1, 1, 0, 0, 1, or 0, 1. So there's the 4 interesting truth table combinations. And this thing is called an RS flip-flop. It's also logical memory. And this particular circuit has a symbol. We'll talk about why it's memory in a second. RS. Q bar. So the symbol looks like this, with the little not inputs, the Q output. And the idea being that when both inputs are high, it holds what's in there. You can either have the Q set to 1 or the Q set to 0. So this is known as a hold. That locks the value into memory, so it holds if the memory is either 1 or if it's 0, and we happen to have the complement coming out as well if we need it. The set, so if we start out in the hold state with both high and we take the set bit low, it turns the Q bit to 1. It puts a 1 in the memory. And if we take the reset bit low, it puts a 0 in the memory. So we can load either 0 or 1 in the memory by taking either reset or set low. And then we can sit here with both inputs high, and it holds the memory. We can read it as often as we want. So we have a mechanism of changing the memory, and we can hold it so we can read it again. So that's how this functions as logical memory, this flip-flop circuit. There's also a related circuit. We built that circuit with NAND gates. We could have built it with NOR gates. Draw this here quickly. B, same thing, X, Y. We'll put the logical feedback into the 2 inputs, and then here X is going to be A or Y complement, and Y is going to be B or X complement. And in this one, same sort of combinations work. We have 5 possibilities. X, Y, 0, 0, 1, 0, 0, 1. And we're going to get 1, 0, 0, 1, 0, 1, goes to 1, 0, and there's both of them high. They're going to give us 0, 0. And as before, we'll focus on the ones where the 2 outputs are complements of each other. Now you can see something here. There's the hold state. Both inputs are low. You can hold either value. If you take B high, you set it. If you take A high, you reset it. So B goes to set. A goes to reset. X goes to Q. Y goes to Q bar. And that flip-flop has a somewhat related symbol. It's just missing the 2 circles on the input, Q and Q bar. It's also digital memory, but it holds the memory when the inputs are low and sets the signal when the input goes high. So the NOR base is low, the NAND base holds the signals on high, sets them when the signals go low. And they're both useful, and they have separate symbols, so you'll find those in circuits.